Good afternoon, everyone. Can you hear me? Can you hear me? Okay, all right, thanks. Okay, so today we will move on to the last lecture for this course, right? So this lecture will mainly to introduce you with the fluid related applications using finite element methods, right? But for sure, for fluid application, finite element methods may not be the best method, okay, which I will slightly inform you later, okay. But the idea is that we can also solve for the fluid type problem, okay, using the finite element method, right? So this is the last chapter, okay, chapter 8, where the purpose is to expose you with some of the fluid engineering problem, right, by solving them using finite element methods, okay. So I believe you have learned this somehow in the CAE course as well, right, which is taught by Dr. Chong, right? So I guess you may have learned a lot from there as well, okay, mainly on the CFD, right? Okay, so since this is part of the syllabus, I will just quickly go through it, okay, on how we can apply the finite element methods for solving the fluid problem, okay. So first is again we will start to the basic theory, okay, where this is the first one-dimensional steady state fluid flow, okay, through a porous medium, okay. So this porous medium can be something like this, okay, ceramics, okay, the sponge and so on, right? So that's a porous medium where fluid can flow through it, right? It can flow through it, okay, but at a certain resistance, okay. When the surface when we set up that particular problem, okay, so we may set up such that since this is one-dimensional problem, we may set up that the flow of the fluid will only go through one directions, okay, from one point going into the system that we intend to solve and then going out, right? So that is the fundamentals of theory that you have learned in the fluid mechanics, okay. I believe you also have learned this before, right? So we again use the basic concept of fluid, okay, where we will assume a conserved mass, okay. So whatever mass going into this particular cube will go out, right, after some time, okay, unless there is something generated inside. So in this equation we will say the mass in, okay, plus any mass generated, meaning to say we will add mass, maybe there is some other pipes that connected to it, okay, that increase the mass at this particular volume, okay. Then you have the M generated equals to whatever that will comes out later on, right? It must goes in the conserved way, right? So in mathematical form, we can again break them down into the density multiplied by the velocity multiplied by the area. So basically this velocity multiplied by the cross-sectional area will give us the volume, okay, per second, okay, per unit time, okay. Then when you multiply by time, meaning to say you get a volume, and then from the volume itself, when you multiply by the density, then you would get the mass itself, okay. So this would represent the mass input to the system, okay. Similarly, you may have the rho Q, where this Q is the internal fluid source, okay. It can be in the form of meter cube per second, okay. So this Q represent the VA, right? So we just assume that they have a Q, then equals to the whatever the volume that is being output there, right? So you have the balance, okay. So again, through this porous medium itself, okay, now we will start to define how the fluid will flow through it, okay. What is the velocity related to the fluid flow, okay, when they are going through a certain porous medium, okay. So you can expect, or you can estimate it through some theory, okay. So again, the famous Darcy laws, okay, that you have learned in the fluid mechanics, okay, comes in, okay. So you have V equals to minus K d psi over dx, right? So this again very similar to the thermal conductivity as well as the displacement functions, okay. So the spring mass, remember, okay, you have the K dx over dt and so on, right? So you have that kind of similar differential terms, okay, to represent how the fluid will change according to distance, okay. So this K, again, you can estimate it through some experiments, or you may get the value from some books or reference, okay. For example, the clay will have 1 multiplied by 10 to the power of -8 and so on, right? So you can enter that, okay. Then from there you can roughly estimate how the fluids will flow through it, okay, through that particular porous medium itself, okay. So from this onwards, okay, this is representing the velocity at the inlet surface, okay. For the outlet surface, again, similar to the thermal applications, okay, you may use a Taylor expansions to predict what is the velocity, okay, at a certain small differential distance, okay. So the x plus dx, okay, at the surface, right? So you can use the Taylor series, and as we have discussed previously, we will just take the normally we just take the first or the second terms of the Taylor series, okay, sufficiently to describe our results, okay. So from that, we will add into our previous equations, okay, equals to 0, and then we will form this particular relationships, right? So the changes should not be, how should I say, because the mass is conserved, so when you differentiate respect to time, then it should be equals to 0, okay. So it shouldn't increase or decrease according to the distance itself, right? Then if we want to expand it for two-dimensional cases, we just extend this particular terms, okay. So you have delta k delta psi over d delta x, okay. Then differentiate this whole term respect to this, right? So this is again a general terms, okay. So when the k itself, the permissibility terms or the constant is a constant, okay, yeah, the permeability is a constant respect to x, then therefore you can bring this out, okay, become a constant outside. So this would be delta psi over delta square psi over delta x square, right? So this is a double differentiations. Okay, if this term is a constant with respect to the x, okay, but then if your permeability change according to the distance, okay, for example you have a long tube, okay, whereas along this long tube itself you may change from clay to other gravels, let's say, okay, gravel, so you mix accordingly, so you assume that it changed from this value to the other value proportionally, then yes, then this would have to change according to the x, then you have to differentiate this term as well respect to x. Okay, same thing for y. Okay, you have these general terms, okay, plus q equals to 0. If you are dealing with a three-dimensional case, then yes, you have also the delta z as well, okay, another terms for that. Okay, so those boundary conditions that we usually apply to our systems would include similar to the thermal applications, you will have the non-boundary fluid head, okay, at the surface. So this head actually represent the pressure. Okay, so if you know what is the pressure, okay, acting on the surface of the maybe a pipe, okay, then that is the non-fluid head at the surface. Okay, you can set that particular surface equals to certain pressure. All right, then also you may have a prescribed gradient or velocity. Okay, you can set this, okay, whether it is changing or as a constant, and also you may also set the surface or the boundary as an impermissible, meaning no fluid will penetrate up in or out of the surface, therefore the velocity at that particular surface will equals to 0, right? So this Vx is just a notation, you can use Vy or whatever it is, okay, perpendicular or normal to that particular boundary surface. All right, next would be the fluid flow in pipes. Okay, previous our applications is referring to the porous material, okay, but then if you are using it for the pipe itself, okay, where inside is nothing except air, okay, then you just enter the permissivity of the air itself. Okay, so basically it's almost no resistance. Okay, we will assume no resistance, and you will move through the pipe, okay, on right? So in this case again we will assume steady state, okay, and irrotational flows, okay, of incompressibles and inviscid fluid, right? So again, very important in this definition is that we will assume that the fluid itself is incompressible. Okay, if it is compressible, then it may be difficult to solve using FEM, okay, finite element methods. All right, so for the ideal fluid itself, we will assume that they do not do not rotate, they will only translate. Okay, then frictions between the fluid and the surface can be ignored, right, most of the time. Okay, even though in real there is frictions, okay, but in our calculations we assume there is no frictions, as well as it will not penetrate through the surroundings of the surface of the body. Okay, so meaning to say, if you have a pipe, right, so the fluid flow will flow through along the surface. Okay, it will not suddenly penetrate out or maybe go separate, okay, from the surface. Okay, so that would create a void. So that is when we assume there is frictionless, so the fluid will smoothly travels, okay, along that part, right? Then again, that is the velocity potential functions that we will apply accordingly, right? So very similar to what we have previously, right? And from there onwards we will use the conservations of mass on two dimensionals, okay, for two dimensional x and y's. Okay, so eventually you get the same equations. All right, so only difference is that the kx, ky, y may be equals to 1, okay, in this case, right? Then it will flows accordingly, right? That is where you use it for a pipe, okay? So now let's see how all this theory is related to our derivations of the finite element model, right? So as you have learned before, okay, for a basic two nodes element, maybe this is a spring or whatever it is, okay? So two nodes, okay? So the potential functions given that we intend to implement to this finite elements is similar to what we always do previously in the structural problem, okay? We always start with the displacement function, right, to be implemented into the finite element itself, okay? So same thing for the fluid. Since this is a fluid, then we will use a potential functions to be applied over here, right? So from these potential functions we can get the shape functions, right, similar, okay? So basically the formulations for a two nodes elements can be applied, okay? Only changes is the parameter that you assign into it, okay? The n1 and n2 values, okay, according to the potential functions that you need to assign accordingly, right? And then also previously for structural problem we use the stress and displacement relationship, okay? We have a stress and strain relationship, then strain and displacement relationship, okay? So same thing here, we will form a relationship between the potential functions itself with the hydraulic gradient, right? So it's given by this, okay? So it's very similar at the end, right? So once we put that in, okay, we can also form like the gradients relationship with respect to the velocity, okay, in order to estimate what is the velocity flowing through based on that particular relationship or conditions itself, okay? So that is derived based on the Dicey law, okay? So we will apply it, all right? So eventually this give us or it will enable us to estimate for the velocity, right? So from the potential we would get the hydraulic gradient, okay, meaning to say the potential the pressure itself, okay, over there, and then from the potential gradient itself we will estimate the velocity, okay? Just like the displacement, we can estimate the strain. From the strain we can estimate the stress, right? So it's very similar, okay? It's only the notation that being used in the finite element equation itself, right? So same thing, if you intend to find what is the nodal potential or the fluid head, okay? Remember fluid head is not the normal head, right? So this is represent the pressure, okay, the potential itself, okay, at any particular arbitrary point of the fluid, all right? So you can use these equations, okay? You can form the fluid flow, okay, instead of force, right? So the P is the potential instead of the displacement, right? So from there you will form this relationship. So it will be AK over L, right? Whereas for the structural we have the AE over L, right? Okay, so something very similar, okay, that you will see, all right? So from that concept, I believe you now can see, okay, how they are actually related and being expand to different application like thermal, and now we mentioned about fluid, right? And as you remember the previous lecture also, okay, I've mentioned that it can be expand for electromagnetisms, okay? So the concept is very similar, okay? Based on the formulation of the finite element itself, okay, those parameter that you're going to insert is depending on the similar differential form, okay, that derivative form or terms that you can insert into the software or maybe the model itself, right? So again, for a finite element model to be good, right? So this is where your knowledge, okay, on many things, okay, engineering terms, engineering knowledge, science knowledge are very important for the estimation of the conditions, okay. For examples, here you may see the applications of deep sea drilling. All right, so you have two pipes, okay, they will bend over here, right? Let's say, okay, so let's say maybe this is moving, so this is the pipe will move as well, right? So at a certain depth, okay, you may want to model the fluid flow at different conditions. So you will see that in this problem itself, it may be depending on the temperature, right? The fluid flow may change according to the temperature. Yes. Okay. So how would you estimate the temperature of the water in the deep sea? Let's say here. Okay. Do you need to dive in to check what is the temperature? Okay. If you know the value of the temperature, you can try it in the chat box, okay, while I will explain the other things before I reveal the answer. Okay, for the second question, what if the temperature is different at the both end? Okay, this point and the other point, maybe this is room temperature, is hot summer now, is maybe 30 degrees Celsius, okay, whereas this is very cold, right? So what if the temperature is different at both ends? What should you do? Okay, temperature at this point and the other point is different. What should you do? You may want to consider the temperature effect on the permissivity of the fluid itself. Okay, so as I mentioned previously, you may need to differentiate respect to the x, okay, which depends on the temperature in this case, right? So you may need to do this, right, if the difference is very large, okay. But if the difference is very small, then you just use an average temperature would be fine, okay. Maybe let's say this is maybe this is 10 degrees Celsius, this is 20 degrees Celsius, only difference in 10 degrees Celsius. So you just use 15, the permissivity of temperature at 15 degrees Celsius, use it for both, okay. You may use that, okay. But if the temperature difference is very large, then you may have to consider the effect of temperature on the permissivity and other expansions or whatever it is of the fluid, right? Next would be, how should you model a moving object? Okay, for example, you have an aeroplane, okay, you have a blade, okay, which keep moving or rotating, okay, but in the computer system, okay, nothing is moving, okay. You draw an object, okay, you may draw a pipe, okay, you say this pipe is moving, okay, up and down, okay, shaking, okay. You want to see how it will affect the flow of the fluid, but how should you model this? Okay, in the computer, this pipe is static, right? So what you need to do is to apply a proper boundary condition, okay, to simulate that particular movement, right? That which I will discuss later on. So any idea what is the temperature of water in the very deep sea? Okay, no answer from you. All right, so we can use the knowledge of water properties, okay. As you know, for water, okay, the highest density of the water occurs at 4 degrees Celsius, okay, because of the structure of the water itself, water molecule H2O itself, okay, which will be in the dense or packed configurations when it is at the 4 degrees Celsius, okay. So meaning to say, if it is the 4 degrees Celsius is the most dense, okay, therefore the most dense water or fluid will will sink, okay, at the bottom, right? So this is how it occurs, and that's why in the real cases, okay, you can see that in rivers and whatever it is, okay, the water only gets frozen at the surface, okay, but not at the bottom. All right. Okay. So now this is how we can model a flow, okay, in a stir tank. Okay, so what you can refer to the link if you want, right, to get some simulations results of this. Okay, so I extract his results from here, okay, where you can actually see, okay, in order to model this actual propeller, okay, which keep rotating over here, okay, to steer this whole particular tank, right? So you can see that the tank design, there is a notch over here, so that the fluid will keep rotating over here and rotating over here by mine design, okay, somehow, right? So he want to see the flow patterns, how it would looks like, okay. So what he can do, okay, is he put a square, okay, and measure what is the actual velocity, liquid velocity at the outflow of the zone, okay. They measure what is the velocity of the rotations, okay. So based on that particular liquid velocity that they have measured, okay, then they assign that the fluid going through this surface will have this particular fixed velocity, okay, to represent that particular steering. Right. So by assigning this type of boundary conditions, okay, or the conditions of the system itself, where this surface will generate velocity, okay, in this form, therefore he can estimate the flow pattern, how it would steer, okay, how the mixture inside this will be being steered, okay, whether it is strong enough to push it to the end, or maybe if it is not strong enough, then you will start to flow like this, right? Okay, so this is how it is being used, right? Again, you can also use the flow analysis in pipe, okay, using Lisa FEA, right? So you can try to use a two-dimensional analysis, okay, just like this, two-dimensional, no need three-dimensional, if you have understand the concept behind it, right? So two-dimensional may be good enough, right? So not necessary three-dimensional, okay. So this is again a two-dimensional problem, right? It's because there involve x and y, okay. So this is the answer when to use two-dimensional, right? But if you are intend to use it one-dimensional, then yeah, maybe that only involve a pipe, all right, which I guess for today's knowledge, okay, most of the people can estimate the fluid flow in a pipe, okay, using the equations, okay, very straightforward, okay. You don't need FEA software, right? But if you have a lot of pipes connected, then yes, okay, the software may helps you to see the relationship, okay, of mixture of different pipe, okay, going in, out, okay, through the frictions laws and so on, all right. And that is where the two-dimensional or three-dimensional analysis may be required, okay. Then next would be the when would you want to use a steady state or a transient analysis, okay. Again, this is a very basic basic questions that you must ask yourself, okay, when you run the analysis, okay, whether you want to run a steady state or transient, okay. What is the difference between steady state and transient? Steady state is referring to the condition when you have run it for a certain time, and remember in control engineering we say you have achieved the steady state conditions, right? So the beginning part you don't care, right? So maybe you open pipe, okay, upon the valve of a pipe, right? So the fluid will start to flow, okay, and after some time it will reach a steady state. So if your intention is only to see what is the velocity during the whole operations, okay, during the whole operations of the pipe, okay, when you open a certain valve, okay, then you can run a steady state, okay, which is very common in the fluid, okay. Even in thermal we usually intend to see the steady state, right? But then if certain cases when you would want to see what is the effect of opening a valve, okay, meaning to say you are analyzing maybe the valve design, okay, the maybe butterfly valve or whatever it is, okay. So when you open it, okay, what is the fluid flow occurs, okay, through the butterfly valve when you start to open from 0% opening to maybe 50% opening. Then at that particular applications you may want to run a transient analysis, okay, to see how the opening, okay, when it opens slowly from 0 to 50% of the valve, okay, the fluid flow will change, okay. You want to see how the fluid flow will change, whether there is turbulence or whatever impact occurs to the valve or other things, okay. Then yes, you may want to run a transient analysis, okay. So remember, any analysis that you would want to run, okay, think whether you need to use one-dimensional, two-dimensional or three-dimensional, or second thing is whether you want to use a steady state or transient analysis, okay. Once you are clear about this, then only you start to form the final element model, okay. You draw your model according to whether two-dimensional or three-dimensional, okay. Then select the type of analysis accordingly and assign all the boundary conditions accordingly, right? So here, as I mentioned earlier, we may have FEM and FVM, okay, finite volume methods, okay. So most of the computational fluid dynamics software nowadays is applying the finite volume methods, okay, instead of finite element methods, okay, to solve for the fluid flow problem, right? This is because the FVM are generally useful to solve a large problem, okay, where you don't need to model like this. You can see if you are modeling a fluid flow in a pipe, okay, let's say this is going in and going out, okay, through two outlets, okay. So you may see that this kind of problem is very small, okay, being confined to certain things, alright. So this is where the FEM is lacking, alright. But for FVM, okay, so you can see that this is an application of FVM, okay, finite volume methods, okay, where the volume may change, okay. You can see that again in these simulations the car doesn't move, okay. What is moving is the boundary condition that you set initially, okay. You may assign or set that there is a velocity or certain pressure difference between two inlet and outlet, okay, and that causes the fluid flow through your model, right? So that would be good if we can use the FVM to a large problem, high speed flow, turbulence flow like the car, right, and other things, okay. So this is where the FVM are good for, right? So any questions so far? Okay, so if you have questions, feel free to put in the chat box, alright. Then next is the fluid flow potential, alright. So this basically is just to go through quickly, okay, that the LISA FEA and on most of the finite element software, they may come with a manual, okay. That manual will tell you what are the formulas, okay, that have been used in their calculations. So if you need a certain type of conditions, okay, and that formula may not be applicable, then you will know that software may not be useful for you to estimate. Okay, this is where your knowledge in the finite element methods as well as the CFD and other things is useful to judge, okay, whether the software is suitable to analyze or not, right? So this is just a quick check from the manual itself. Okay, it can be used, okay, to simulate the flow by using the fluid potential, okay, meaning to say you may set pressure, certain pressure at one end and another pressure at the other end, okay, and so on, right? And you can see that the assumptions for this is only for the incompressible, irrotational, and inviscid flow, right? So if you intend to simulate air, okay, flowing through a pipe, then this may not be good, okay, meaning to say you will get a lot of error, right? Because the formulation and the manual already mentioned that they will calculate based on the assumptions that the fluid is not compressible, right? So this is where you have to read the manual, right? Then also for sure, as we have learned, okay, we have mentioned previously, they can be applied for no boundary condition, okay, fluid flow, or maybe the zero velocity potential difference, okay, at the boundary condition at the surface itself, right? Then these are the formulas, okay, or equations that may use, okay, to generate the velocity and the dynamic pressure, okay, being estimated for your informations, okay. So you will at the end able to estimate the velocity and the dynamic pressure, okay, from what you insert in, right? So if here they mention that to obtain the dynamic pressure, what you need to specify is the fluid density, okay. With the density, then yes, they can estimate the pressure, okay, the impact of the fluid towards the surface itself, okay. So that is where it is useful. Otherwise, it may only generate a velocity for you, right? So this is where the manual play an important role for you, okay, to understand, right? Because LISA FEA mainly use FEM methods, okay. That's why they only applicable for incompressible fluid, right? So again, for incompressible fluid, this is the general equations that we always use, okay, from the basic of mathematics, Navier-Stokes equations, all right. And this is the again from the FEA software, okay, LISA FEA software, okay, that the formulations of the elements, again according to degree of freedoms, okay, where at the mid side there is only 2 degree of freedom and so on, right? So this is how you can explore, okay, further, okay. Next would be the questions of when to stop, right? It's because when you are trying to solve for the fluid conditions, okay, when should you stop, or when the software should stop, okay. So generally the solver or the software itself will finish when the relative change in the nodules fall below the convergent tolerance, okay. Generally is 0.01, okay, but this convergence tolerance you can always change on your own, right? If you want to use very high, okay, meaning to say we call it as relaxation factors, okay. So every time after you get the value, you multiply by a certain factors, okay, then it will change faster, right? But then if it is changing fast, okay, then it will cause sometime oscillation. It will move to the negative side, then you have to move back to the positive, negative, positive, negative, and so on. So if it fail to converge, the best way is to reduce the factors near to 0, right? Make it smaller, right? So that every time it will reduce a little bit, and so on, right? And other cases would be if the solver failed to converge, they may have other factors. For example, they there is an unsteady flow, meaning because in the FEA software or maybe Lisa software itself, the flow itself is being represented by the mesh, right, to the relationship between nodes to the other nodes, right? So if there is a lot of turbulence, therefore uh, the the potential or the potentials and the velocity that they generate, okay, may not be static, may not become steady, okay, will keep fluctuating every time it's calculate. Therefore the solver may not able to solve, right, or do not converge, right? Same thing if there is a sharp changes, there is insufficient constraint, okay, on the velocity as well as the pressure side. Okay. For the type of fluid, again, as we mentioned, we are we are dealing with incompressible fluids, okay, and there are three types, okay: Newtonian, pseudoplastic, and Bingham. All right, so there are three types of fluids that you may want to model, right? That can be modeled in the FEA, right? Okay. So what is the Newtonian? Newtonian fluid is the one that will give you this curve shape. Okay, the semicircle type of shape, right? Whereas for the Bingham fluid, okay, if you move, okay, like this, then the middle part is almost flat. Okay, that is Bingham, right? The pseudoplastic is the one that is in between, right? So you can see that from here you see the density and the description of the equations, okay? You can see that the shear rate, okay, between this will change, okay? And from that particular shear rate itself, basically you may able to identify what is the shape, okay, of the fluid, right? So if you want to model this one, then you have to apply the proper viscosity data, okay, to model the conditions of the flow, right? So you may see this paper, okay, they use some common cooking materials, right? Ketchup, mayonnaise, okay, honey, and so on, and see how it actually change, okay, the shape itself, right, from Bingham to the Newtonian, okay, the non-Newtonian and the Newtonian fluid, right? So before we end, I will just go through quickly on several applications, okay, which have been applied by several lecturers, maybe, okay. So this is published by Dr. Chong, right? So his application is to design a marine propeller, right? So this is a propeller that he intend to have, okay, a physical model. He scan it, okay, and from there he reconstruct the model, and from that he can start to see, okay, which one will give the best effect, right? So he may turn the pitch angle, right, the scale angle, the scale angle, the right angle, okay, different models of it, okay. Then he will form a space which is large enough, assuming it's large enough, okay. Like for example, remember you have to set the boundary condition, right? So you may have a large enough volume, okay, in your simulations, and when this spin, okay, nothing is spinning, right? So you have to tell the fluid to flow through it, right? So when it is so-called spinning, okay, so he can check, okay, what is the efficiency, okay, the thrust efficiencies, okay, and the coefficients, okay, between different models of the propeller, okay. Second would be another application of CFD to design the length of needle, right? So this is by Dr. Sufyan, okay, on checking what is the suitable length of needle or nozzle. Okay, so you can see this is a long tube. Okay, long tube, right? Long tube over here. Okay, this part. Okay, so this application is a spinnerate. Okay, where it is being used to generate or to manufacture the nanofiber, right? So this is a liquid, okay, chemical liquid, okay, flowing through, and when this liquid drop into the water, it will get the form, okay, of the fiber itself, okay, in the hollow. Okay, so what he intend to produce is to produce a hollow fiber, okay, something with a hole in between, okay, small fiber, right? So what he would want to analyze is that because of the fluid is coming into the end of the nozzle before it goes out from one source, right? So there is a possibility of rotations and turbulence, okay, if it is, right, flowing through the needle. Okay, so his intention is to check which length of the needles will give the best results. Okay, so eventually you can see that this is nozzle 39 mm. Okay, when it is short, okay, 34 mm, then the generated or the fabricated hollow fiber will have a different thickness. You can see one side is thick, the other side is thin, okay, because of the velocity, okay, going through different surface, okay, due to this inlet, right? So eventually when the length is long enough, okay, the flow becomes stable, okay, and you form a quite uniform thickness of the hollow fiber, right? Next would be another applications to estimate the velocity and pressure drop across a cyclone. So this is a laboratory size of cyclone. Generally, cyclone is mechanisms, okay, that is used to separate solid particles from a fluid, okay, solid particles from a fluid, right? So you may have an air carrying solid particles, okay, so for example you may have a flour, right, maybe not, or maybe sugar, right? So this sugar is being brought by air, okay, you have the pneumatic carrying blower, right? So you blow the sugar to move from one side to the other side, okay, so by blowing, then at one end you may want to maybe collect, okay, or maybe to collect it. So if you want to collect them, then you may need a separator, so this may be one of the separator, okay, but for sure sugar cube maybe too big, okay, you don't need a cyclone like this, right? So this is one type of separator, mechanical separator that you may use inside this separate cyclone, okay. It's actually called cyclone because of the actions of rotating, right? So what is happening is that inside there is nothing, okay, just an empty barrel, okay, with a converging end, okay, like this, okay. So what we do is we will blow the air, okay, that carry maybe a certain particles, solid particles, blow through it. So assuming this is the inlet, okay, so you will blow and it will start to rotate, okay. So the rotations will go down, okay. When the velocity become slower and slower, therefore the carrying capacity of the air get reduced, meaning to say the solid particles will now start to flow down, okay, due to gravity, okay. The air will not able to carry out anymore, just like a leaf, okay. If you see a leaf, okay, if you blow it with air, it will start to fly, right? There is a carrying. But if the air is at the reduced velocity, the leaf will not fly, or we will start to drop down, okay. So same concept, the solid particles will be carrying in, okay, with a high velocity, but then when it start to rotate, okay, just like cyclone, then at this particular end the velocity is largely reduced, okay, and at the end it becomes zero. So eventually all the solid heavy solid, it will start to drop down due to gravity, whereas the air will continue to flow out, okay, through the middle. Okay, the faster will be at the side, okay, the middle will go out, right? So this is the velocity distributions as well as the pressure distributions, right? So this is where the simulations and the measurements, okay, for this laboratories equipment, okay. And if we want to predict the original object, okay, that is lab size, okay, but in the industry, in the factory, is actually very large, okay. So in order to predict the large scales of object, okay, what you need to do is you may need to use this knowledge, okay. Again, you have learned this in fluid mechanics, okay, similitude theory, right, which mainly depends on Buckingham Pi theorem, right? So these two so-called constants, okay, must be equals, okay, for your model as well as your prototype, okay, for your model as well as your prototype. So they must be a constant, right? So if you intend to make the model smaller, okay, if you intend to make your model much more smaller, okay, than the intent size, okay, then you may have to reduce the other parameter, okay, in order to maintain the you may need to increase the other parameter, okay, in order to maintain the same constant, right? So it depends on how you want to model your situations, right? So this is what it looks like in real case, okay. It's very big, okay. You need a stairs to climb up, all right, and this is a factories, okay, and this is the roof of the factories, right? So the air carrying some particles, okay, in a powder form, sort of powder forms, okay, you get into it, okay, and spin through it, okay, and go up, okay, and this is the fan to the fan, okay, being sucked by the fan, right? And then most of the particles will now being dropped off over here, right, at the bottom, okay, on the other side. So you may not see this because being blocked by these pipes, right? So any questions so far? If no questions, that would be the end of these sessions, okay, basically. So before we end these sessions, okay, so I just want to quickly brief you about the final exam, right? So in your final exams, because this is an online final exam, so I would set the questions such that you may need to calculate depends on your matrix number, right? So let's say if your matrix number is something, maybe this is 0 0 1 8, let's say, right? Okay, right. So therefore you will get P equals to 0 plus 0, okay, which is 0, right? So, and then this will equals to 10C, 10 times C, okay, 10 times C, C is 1, so it's 10 plus D, 8, so this may be give you 18, okay. Then the I is C plus D, so 1 plus 8, okay. You don't tell me this is 18, this is 9, right? Okay, so this is how you can calculate your parameter and use it for your calculation in the exam, right? So I hope that will clear for you during the exam time, right? Okay, so if you don't have much more questions, then we will end these sessions and this course, okay. But before we end, right, so maybe probably we would have the last test, okay, the much delayed test next week, okay. So the test will cover from what we have before the test one until what we are now, right? So quite general things, right? We would do it on next Thursday. Is it okay for you all, or you have a lot of still have a lot of tests coming in? If no, then we will now set it on next Thursday. Okay, test 2, right? And that's all for this course. All right, so feel free also to give feedback, okay, if you have any on this course, okay, how it can be improved, any comment on this course, feel free to write in the WhatsApp or maybe in the Google Classroom, okay? And also don't forget to fill in the PK07 in SMP, okay? SMP, you have to fill in the SM, the PK07, the course evaluation in the SMP, which has been open since yesterday until 15th of July, right? So feel free to do so, okay? So that's all from me. If you have more questions, don't hesitate to contact me through WhatsApp, right? So that's all. See you. Bye bye.